Good morning, everyone. From sunny Germany, this is again Rita, and I'm happy to welcome you to the fifth session of our European Science Bootcamp number 8. Thank you for joining us again this morning. The title of today's webinar is Tautomers Conformers and pKa, Useful QM Approaches. And it is my pleasure to introduce today's speaker, Dr. Stefan Ehrlich. Stefan works as Senior Application Scientist for Schrödinger since 2016. Before that, he did a postdoc at the University of Bonn, where he cooperated with Bayer Healthcare to predict protein-ligand binding affinities using graphics card-based quantum mechanical methods. He received his PhD from the University of Münster in Germany, where he was working on non-covalent interactions in small organic systems in the group of Professor Dr. Stefan Grimme. A chemist by training, Stefan has a broad background in the field of computational chemistry with a focus on non-covalent interactions and quantum mechanical methods. As usual, if you have any kind of questions you'd like to ask Stefan, please type them into the Q&A field or also in chat to me. That works also fine, and we will answer them at the end in our Q&A session. And of course, as usual, if you get interested in what you see today and you don't currently have a license for our software, please feel free to request an evaluation copy by emailing help@schrodinger.com or filling out the form on our website. Now I will pass the controls over to Stefan and we can get started.
Yeah, good morning, everybody, and also welcome from my side. And thank you, Rita, for the nice introduction. So let me just share my screen. I hope everybody can see my slides okay.
Yes, thank you.
All right, so today's topic will be Tautomers Conformers and pKa, and we will talk a bit about what kind of QM, so quantum mechanically based approaches, we have in our software suite that might be helpful for you. So this is something we are actively working on. And I'm kind of excited to share a few of the new tools that we have been developing. The first one will be something that we call Autocons. So this is a multi-level workflow that lets you enumerate tautomers and conformers and also gives you a QM-based ranking of those. Now, why is this useful? So here I have prepared a few tautomers of a drug molecule, and the challenge for you now would be which one is the most stable one. Now it's not easy to see. Some of them look a bit unreasonable, so if you have chemistry training, you'll probably pick out that the ones here at the lower left side are probably not something that you would see in water, while the ones at the top all look quite reasonable. And actually, you wouldn't be too wrong if you said that. So the first two are more or less equivalent in solution. The third one is a bit higher in energy, and from there, basically, you have tautomers that are so high in energy that you will probably not really see them in solution easily. Now, this is actually an example where we have ran a few calculations on. So we had this in a collaboration work with a customer some while ago, and this kind of molecule is actually a known class of kinase inhibitors. So there's a patent filed for this. Feel free to look it up. And if you know a bit about kinases, you might have recognized from the start that we have here in this region the part of the molecule that actually can form the hydrogen bonds with the hinge, and we really need this kind of donor-acceptor-donor chemistry here, otherwise it will just not bind. Now, since it can tautomerize so easily as we saw before, there are also, of course, tautomers that do not bind. Now, we went ahead and we used FEP. So if you joined yesterday, maybe you learned something about MD and FEP, which is our molecular dynamics-based tool to predict relative binding affinities. So we used this on this system, and the results were basically not as good as we would have expected. So usually we see something that is below 0.5 kcal in the binding relative binding affinities and accuracy. And as you can see here on the right-hand side, that is not what we saw. So you have the FEP here on the y-axis basically, and you see that this group of molecules here are actually predicted to be more potent than an experiment by FEP. Now this kind of points towards an error that has to do with kind of a missing penalty that the molecule has to pay before binding to the protein. And actually that missing penalty in our case is the energy that the molecule basically has to pay to get into the tautomeric state that can bind to the protein, as I have told you on the previous slide. And if we actually calculate that by QM and add it on top of our FEP results, we get a much nicer result, as you can see here on the right-hand side. So all those outliers that we had before in this region here have been shifted up to basically lower binding affinity and now agree much better with the experimental result. Now, what's the reason for this? Since we're doing structure-based modeling, we can actually look at the structures and see what's happening. And it is kind of connected to this R group here. So if we have something small in this position, the oxygen here can be nicely solvated. I get an internal hydrogen bond here, and I basically get my hinge binding pharmacophore here. So again, donor, acceptor, donor. So that's perfectly nice. Now, if I put something bulky here, like this much more bulky aliphatic group, I actually force the molecule into a different conformer. So I force over the oxygen, and that's very unhappy here because it's not solvated, so it's a bit more buried in the protein. So it tries to make at least a hydrogen bond to counter some of the missing solvation. And yeah, it does that, and by that it forces the molecule to tautomerize into the state that actually doesn't bind to the hinge. So that's the kind of complicated and complex chemistry that you can see with tautomers, which is why we think that actually having a tool that can evaluate those on a QM level can be quite helpful in design. Now let's actually switch right into the software and look at how this works. Now here I have a very, very simple molecule, which is 2,4-dihydroxypyridine. I just drew it, so generate it however you like. And the tool we are looking for is the QM-based, so QM conformer and tautomer predictor. You can find it easily if you browse to Jaguar. Here it is. So I've set it as a favorite, which means I can just access it here from my quick bar. And it's a very simple tool. So basically just pick if you want to generate tautomers or conformers or both. Say how many structures you finally want to keep, and it usually runs in water, and I can just go ahead and run it. Now, if we want to dig a bit deeper into how it works, we can actually go here to this little triangle, go for the custom configs, and this opens up a text editor that gives me an idea about how the workflow goes. So the first part here would be to generate all the tautomers, then it runs some semi-empirical calculations, which are PM3 for those of you who have some background. Then, based on those, it actually throws away many, many structures, keeps the 10 best, generates conformers, and then runs first a QM optimization on a quite low level of theory, and then again it keeps the best structures and goes into a more accurate QM calculation here. So what you get back as a result in the end looks something like this. So you see here I have a group. This is sorted by the final energy in solvation, and as again people with chemistry background might have expected, this keto form here is the most stable. The next one would be the enol form, the corresponding one. I have a double keto form for this one as well, and basically then it starts to get a bit more unreasonable. Now, if I want to look at the energetics of this, there's a nice little tool that is always useful when you're doing QM calculation, which is called the Jaguar Energy Converter. So I have it here right in my top You can search for it as well in the tasks menu. What this does is it actually calculates the energy difference in kcal per mole of everything you have selected. So you see I have selected all those structures here and gives it back to you. So if I just select this and click this once, you don't see anything, but the property, the relative energy property, has actually been added. And if I just click here on the title, I get my workspace properties. I can go ahead, add. I will search for relative. And you see I have here solution phase relative energy. Just add that, and as you see, it's now also added to my workspace, and I can again switch through the structures and see how big the energy penalty would be to reach another of those tautomers. All right, let's go back to the presentation and let's have a look at the next topic. Another thing that people, of course, are interested in and that we have very useful QM tool for would be pKa calculations. So our tool is called Jaguar pKa. Jaguar is our quantum chemistry code that, by the way, also runs the calculation for the conformer and tautomer generations. And we will start a bit at the basics of pKa prediction that you can do in computer-aided drug design. Now, this is something I think most of you have probably seen. This is a titration curve where I actually stand in a lab, titrate this. Maybe you have done some of those in your undergrad lab courses, and those 2 points here are actually the ones that you measure in the lab. So you get, in this case, 2 pKa values for that molecule. Now, of course, it is not that easy. Now, if you would have a closer look at what we actually have in the flask, then of course we always have an ensemble of tautomers and conformers for each of the different charge stages that we visit during our titration. And while those things we measure in the lab would be called macro pKa, we can actually define something that we call micro pKa, which are the transitions between all those microstates that you have here. So between one tautomer at charge 0, for example, and another one at charge 1. If we go and look a bit deeper, we can even make it a bit more, I'd say, well, not complicated, but more accurate, and go down to what we would call a nano pKa. So while you see here in the bottom part that the macro pKa is basically calculated by calculating all the micro pKa's between all the different tautomers and conformers that we have at certain charge stages, and we just calculate the macro pKa as a sum over all the micro k. We can actually do that as well for the micro pKa. If we pick a specific tautomer and go ahead and generate all the conformers for that specific tautomer, then we can sum up over those nano Ks, which are basically the equilibrium constants between a certain conformer of one tautomer and another conformer of that tautomer at different charge states. And you see, very, very similar to what we do for the macro pKa, we can also do that for the micro pKa. Now I am only telling you this. Very simple. What we can currently calculate in Jaguar pKa are micro pKa's, which are based on nano pKa. So you can do actually a conformational sampling and get all the relevant conformations for your microstate, but we currently cannot calculate macro pKa's out of the box. But I will tell you a bit about what we're doing here currently a bit later. Okay, so how does Jaguar actually calculate those values? What you have to do, and I will show you in a bit also how to basically do that in the interface, you have to pick a pKa atom. As you remembered, we can only do the microstate, so you as the user have to pick what microstate is interesting for you. So which would be the most relevant one for the drug molecule that you're actually looking at. So here it's quite easy, pyridine, so we pick the N, of course. Everything else will probably not get protonated. And after that, actually, you can start the workflow, which will generate the protonated or deprotonated form, depending on which you put in, do the conformational search, do QM optimizations, and then do a higher level energy calculations on those structures, calculate the solvation energy of both states, and then what you get out of the DFT part here is you get a raw pKa estimate, which is basically just the energy based on the energy difference between the protonated and the deprotonated form of your molecule in solution. What we also add here are empirical parameters. Now, why is that? Accuracy-wise, this is a difficult calculation because we would like to have an accuracy that is below basically 1 unit in the pKa, which means 1 order of magnitude in the equilibrium constant, and that kind of translates into an accuracy of 1.4 kcal per mole. Now, that is something that you do not so easily reach with computational models, even with DFT, which is why we actually go ahead, and since we want to be more accurate, and add empirical parameters here. Those are based on functional groups. So the code does a substructure search basically for your molecule and looks how it compares to molecules where we have actually experimental data and that we have parameterized the code on. And here you see a snapshot of all the functional groups that are in there. That means that if you have something that's similar to this, you will get a very high accuracy with Jaeger pKa, but Jaeger pKa, since it's an ab initio method, will also work on novel chemistry. That means even if your kind of chemistry is not represented here, it will give you probably a good estimate, but it will not be as accurate as if you are close to the chemical space that we have actually parameterized. So what does it look like in the end? If you care to take a look at the output file of the calculation, you actually find something that is very similar to what you see here. You see in this case, I actually have 5 conformers for both the protonated and the deprotonated form. You can actually load the structures. You can also find them if you load the full result of your calculation, but those are the structural files that get used in the calculation. And as you see here, I have a table. Now, what does this table tell me? It tells me what kind of chemistry the program has recognized. So the best guess that has the highest similarity actually to the chemistry we are looking here at would be an amidine, which is quite obvious actually. So this here is a pKa atom, and this looks very much like an amidine. And then there are other ones that are less well represented basically by the structure we are looking at. And as you see, I also get here percentage scores for the contribution that the pKa that this shell, the pKa of this shell actually has to my final pKa value. So if this would be a pure amidine, I would get a pKa of 8.28 in this case. But as you can see, we have other things that are also similar, and what the code does in the end is it sums up with relevant contributions and gives you an estimate here. And we have seen that this actually is much more robust than just picking the top shell, which is what we basically did maybe 2 years ago, so previously. Now for some more examples, why would you want to run a very, very expensive QM calculation if you can have an empirical model give you the pKa in the order of a few seconds? Now this is an example where it actually makes a difference. And a difference comes from the fact that empirical models usually don't take into account 3D structure. Since we're doing a ab initio method, so quantum chemistry-based method, we do take into account the structure. And as you see, those 2 stereoisomers here basically have different pKa's in the experiment. If we run EPIC, which is our empirical code, we get the same prediction for both stereoisomers. If we go ahead and run the Django pKa calculation, we get different pKa's that are much better in line with the experimental values. Another example would be here, this more complicated molecule where we again are looking at the nitrogen. And again here you see that basically EPIC gives very, very similar results for all. It even doesn't really recover the effect from this methyl group that is added here. And if we basically plot the pKa, you see that Jaguar, which is the red line here, very well reproduces the experimental trend, while EPIC is basically a straight line and would say within the error that EPIC usually does, those four structures are basically equivalent in pKa. Now let's switch back to the software again. I've prepared another example, which is basically the one that I've already shown you. And I will actually bring up the structure and go to Browse, Jaguar, pKa. And what you get is this kind of panel. It's slightly more complicated than the previous one. The things you have to do are the following. So as I said, you have to pick out the pKa atom, which means in this case, I'm just going to double click here and pick one in my structure. Since I am looking at the protonated structure and the process I want to look at is basically deprotonation and protonation of this nitrogen, I'm going to pick the hydrogen here. If I was looking at the deprotonated conformer, I would of course go ahead and pick the nitrogen. What would happen if in this case here I picked the nitrogen, I would actually try to protonate the nitrogen again, so we have the double protonation, which is not the process I would be interested in this case. So you have to take a little care which atom you actually pick in this. As you can see, it pops up here. I've picked the hydrogen. It automatically recognizes that I have +1 charge. And here, this part is probably the more important one, which means that you can perform a conformational search on my input structures. So if you have more complicated input structures, and I've already shown you, I think, that this is important, be sure to make the conformational search. Here you can actually pick how many conformers you want to use. If you increase that, it's going to be more expensive. And this is the energy window above which conformations will actually get discarded. Now I can go ahead and run this again. Not going to do it because it takes some time. The nice thing about this, it really parallelizes well because you can run all the independent QM calculations on different cores on your cluster. What I get out would be something like this. So you see, I actually get a group. So I've called it pKa example here. And directly in the group, I have the lowest protonated and deprotonated conformer. So let's just go ahead and add some labels. I don't know where they went. Usually they are already there. So in our case, we would go for a custom label and say pKa water. Okay, there we go. So you see in the protonated form, I get the label for the hydrogen, 8.1. In deprotonated form, I get the label for the nitrogen, which is also 8.1. What I also get is I get all the protonated and deprotonated conformers. So this can give me some idea of the conformational space that was actually covered and of the conformers that might be relevant in my case, and that have been contributing to my final pKa values. All right. Now something that is a bit in the future, which will hopefully be released this year. Now, as you can imagine, it is quite useful not only to have the micro pKa's, but maybe also to get an idea about what would be measured or what has been measured in the experiment. And for this, we would, of course, need to calculate the macro pKa. Now, as you have already seen, you have to decide as a user currently what the pKa atom is. In the case of pyridine, it's quite obvious. In the examples I've shown you, it's also quite obvious. But there are a lot of molecules around where it's actually not that obvious because you have a lot of tautomerism. You might have multiple protonation sites that are very similar, where you as user are basically not sure which is the one. And also, if you have multiple protonation sites, it is very, very likely, if they are very similar, that all of those contribute to the macro pKa state that is, of course, measured in the experiment. Now, just for this molecule here, if you do the exercise and enumerate all the possible tautomers, you see that we get basically large numbers of tautomers here. And you can read it up actually in a publication that we have in 2017. Now, if we take a look back at our titration curve, the property we are after is no longer the micro pKa, but the macro pKa's here that were measured in the experiments. And mathematically, as you have already seen, this is really, really simple. We just have to calculate all the micro constants between all the states that we have at every charge. Then we just plug them into this very simple equation and we get our macro pKa. Of course, this is something that has been done. So you can do it manually. If you have very simple molecule that does not have too much complicated tautomerism, you can just basically by hand enumerate all the states, calculate the pKa's for all those micro transitions, and then you can sum it up and you get macro pKa's that are actually quite similar to what you would expect, what you would get in the experiment here. Of course, if you have more complicated tautomerism, that's not a viable option, so you would like to have something that does this for you in a reproducible way. So what we need for the macro pKa are a few components. We need to have a good DFT model. I think we have one. I already shown you that is also efficient, so Jaguar is quite fast. We need a good implicit solvation model, so we have the PBF, which is a good solvation model. We need a good micro pKa model that puts the two together to predict the micro pKa, and we also have that. But we also need an efficient tautomer generator. And by efficiency, I do not mean that it has to be fast enumerating the tautomers, but it has to be efficient in a way that it just enumerates the tautomers that are actually relevant for our macro pKa. And this, if you think a little bit about it, is not as trivial as it sounds on the first glance. Now we will make a huge step very, very far away from the world of pKa's and the world of quantum chemistry as it's applied usually in drug discovery. So those of you who have a slight background in theoretical chemistry, so hardcore quantum chemistry, might recognize this. For the others, I'll give you a very short glance on what this is. So if we calculate, if we do quantum chemistry calculations, let's put it this way, we usually base our calculations off one single determinant, so one single distributions of electrons in the orbitals. So DFT does that. Most of the methods we use nowadays do that. Now there's something that's called full configuration interaction. That means as we have in pKa multiple tautomeric states that might play a role for our macro state, of course also if we look at it at an electronic level and look at electrons and orbitals, this is not the only representation of our wave function that is relevant, but of course there are other representations and they can play a bigger or smaller role in the representation of our molecule. Now if we enumerate all of those, so put all the electrons and all possible combinations into those orbitals, we get something that's called full configuration interaction, and that would be accurate. So this would be basically the perfect solution to the Schrödinger equation, and we would get the correct energy. Unfortunately, there's very, very many of those combinations, and we have a combinatorial explosion, which means we cannot treat systems with this that are bigger as benzene, basically. Now, people have thought about this a long time and have come up with a solution for this, which they call complete active space. Now, if you think about it, actually, I'm not really interested in those electrons that are very, very close to the nucleus, but we are already usually only interested in valence electrons, which means I could say, okay, those orbitals here are so high in energy that they are probably not relevant. Those electrons here are so low in energy that they are also not relevant. And I'm just looking here at the middle, which is actually the part that's interesting for chemistry. And so I enumerate all the combinations in this active space, and I get less combinations and break that down to a manageable number. And this basically is exactly what we put into our tautomer generator. So what it does is it actually defines active sites, which are atoms that can accept or donate a proton. And then we have the protons, which correspond basically to our electrons in the previous picture, and the active sites, which would correspond to our orbitals in the previous picture. And with this, we actually have a rigorous way of enumerating all the tautomeric states that might be chemically relevant. Of course, we have to put something in. So we have pre-generated protonated and deprotonated tautomer sets here. But in this way, we can actually break down the vast space of possible tautomers into something that is chemically reasonable. And if we apply this to this kind of complicated molecule that we already have, you see that actually the number of tautomers that get into the calculations because we think they are relevant is much lower than what you saw on the previous slide. And you can also see that if we do the exercise, we can actually calculate macro pKa states that are very close to the experimental value with this. So this is not yet available, so stay tuned. It might come out just this year. So I hope that I could, if you didn't know already, tell you that tautomers are important. So you can actually use our AutoConf tool in Maestro to get a handle on complex tautomeric states, get an idea about how they relate to each other energetically. And it can be very helpful to identify the correct tautomer. And if you have multiple tautomers that might play a role in your system, also calculate accurate penalties for structure-based design. So as example, I have given you the FEP example, but also if you do an MD simulation, for example, you might want to have correct tautomers that can do the correct interactions. I hope I could also show you that Jaguar can currently give you accurate micro pKa's. And the question I always get on this is, when would I use this? So you should look into QM-based pKa predictions when empirical models fail, of course, and when you think they might fail based on the 3D structural effects, or if you have quite novel chemistry. So empirical models are usually trained on specific chemistry, and they, like basically every machine learning model as well, tend to fail if there is something very new that they haven't seen before. So if you're concerned about that, run it through Jaguar pKa and see if it actually corresponds to your empirical predictions or not. Also, if you want to have very high accuracy, so something that's below 1 pKa unit, you will have to turn to QM-based pKa predictions. And of course, it is always most useful when your pKa is around 7 and you want to know what state your molecule actually is in. So if you have a very clear prediction of a 12 or a 5 from your empirical model, then it's probably not worth looking at it with Jaguar pKa. And yeah, since it's QM calculations, they can actually take some time. So keep that in mind. Luckily, they parallelize very well by now. All right. Thanks everybody for joining. This is already the end of the presentation. I hope you learned something regarding tautomers and pKa, and I hope you also like to try out our tools. So I'm open for questions.